Hello everyone. So we have a question here which says that the number of microstates corresponding to the atomic term symbol 4F is. So we know that the basic notation for a term symbol is L superscript to S plus 1 and subscript is J. Okay, so we know this. And this 2S plus 1 is the spin multiplicity, okay, while the subscript J is the spin orbit coupling, okay, or the spin orbit interaction. Now we have been given the term symbol 4F. So from here we very well know that 4 corresponds to 2s plus 1, the spin multiplicity. So the spin multiplicity here is 4, 2s plus 1. So what should be s? So 3 divided by 2. So s is 3 divided by 2. That is spin is 3 divided by 2. Okay, we got this number. Now we have the state symbol as F. Okay, F. And from this term symbol, we also know that there is a correlation between L value and the state symbol. That also we have learned. So L is what? L is the orbital angular momentum or the resultant orbital angular momentum. And the correlation states something like this. So we have the L values starting from 0, 1, 2, 3, 4, 5, 6, 7. And the corresponding state symbols. These are represented as S for 0, P for 1, D for 2, F for 3, G for 4, H for 5, I for 6, and K for 7. And from here we can see that for L value 3, the corresponding state symbol is F. So we have the F symbol here in our question, which corresponds to a L value of 3. Okay, so from here we got the L value as well. Now, the important thing to consider in this question is that we are being asked the number of microstate corresponding to the term symbol. Okay, so we have to answer about the number of microstates that is applicable for this particular atomic term symbol. Okay, and for this particular atomic term symbol, the number of microstates will be calculated through the degeneracy formula. And this degeneracy formula states that the number of microstates can be calculated as a product of spin multiplicity and the orbital degeneracy. Okay, so this is our spin multiplicity that we already know. So 2L plus 1 gives the number of possible orientations for the orbital angular momentum. That means whatever is the value of the resultant orbital angular momentum, so how many kind of orientations are possible for that particular value. So we have L equal to 3 here. So in what manner, how many kinds of orientations for L is possible? So for predicting the number of orientations possible for L, we have this formula. We know that the resultant orbital angular momentum is predicted through the minus L to plus L through 0. This gives us the number of orientations possible for the orbital angular momentum. So if L equal to 3, then we have minus L to plus L. That means we have minus 3 to plus 3 values, and that goes through 0 also. So we can have plus 3, plus 2, plus 1, 0, minus 1, minus 2, and minus 3. So you can see total how many? 1, 2, 3, 4, 5, 6, and 7. So for L equal to 3, we can have 7 possible orientations. And exactly this value of 7 is obtained if we multiply 12 and then add 1. So if we do 12 plus 1, then also we get 2 into 3 plus 1 is equal to 7. So this 12 plus 1 gives us the number of possible orientations for the orbital angular moment. And the product of 2s plus 1, spin multiplicity, and 2l plus 1 will give us the number of microstates for a particular atomic term symbol through this degeneracy formula. Okay, so we can very well do it. So what is our spin multiplicity? Spin multiplicity here is 2 into 3 by 2 plus 1, or you can directly see from here that is already given 4. So we have 4. And then what is 2l plus 1? 2l plus 1 is 7. So 4 multiplied by 7. And this comes out to be 28. So we have 28 microstates for the atomic term symbol 4F. Okay, so we have an option of 28 in option 3. So that will be our correct answer for this question, that is 28 microstates. So specifically in this question, you have to take care that the question does not ask us for the microstates of a particular electronic configuration, okay? But we are being asked about the microstate for a particular atomic term symbol. So there is a difference between these two. So for microstate calculation corresponding to an electronic configuration, we need to consider the entire subshell configuration, okay? And in this case, for electronic configuration considering the subshell, the calculation of the entire subshell configuration, we need to apply the factorial formula, okay, which you must have previously come across while studying about the different microstates and their calculations. So we have that factorial formula, if you remember, that n factorial r factorial n minus r factorial, where we calculate the twice the number of orbitals and then the number of unpaired electrons, and then subtracting these orbitals minus unpaired electrons and taking out their factorials and dividing like this. So this formula is applied only for the electronic configuration where we have the subshell, entire subshell configuration for calculation of microstates. While in this question, if you see carefully, we are being asked about the number of microstates for the single atomic term symbol. And for this, we have to apply the degeneracy formula and not the factorial formula. Okay, so I think I discussed this because there could be some level of confusion when students attempt this question. So there shouldn't be any confusion whereby we are being asked about the number of microstates corresponding to a particular atomic term symbol. Okay, so I hope this explanation was clear to you. If my videos are helpful to you, please like, share and subscribe, and please let me know what you want to learn next in chemistry in the comment section. Thank you so much.